The next idea that we're going to look at is what happens when a disk either speeds up or slows down. So let's just increase the velocity. And here, it's as time goes by, it's spinning faster and faster. And we can also slow it down so that as time goes by, it slows down. And it can even change direction. So here then, this disk is not, what's happening is that the disk is accelerating but rotationally. And this kind of acceleration, we're going to call that rotational or angular acceleration. So again, as time goes by, the velocity or the angular velocity is changing. In the next part of our discussion, then we're going to be looking at how an angular velocity changes. So you have a wheel that's rotating, and let's say that starting here, the wheel had some rotational angular velocity. Let's call that 1 omega initial, spinning at some initial rate here. And by the time the wheel gets to here, so this is the radius here, by the time the wheel rotates to this point, so this amount of time goes by, and now the wheel, the point on the wheel is going to be at this location, and let's say for example it's spinning faster, so it's going to have a larger angular velocity. So what we're comparing here is the rate at which the velocity changes to the amount of time that goes by. So in the simplest case, we'll say that we're going to call this the angular acceleration, and that's just going to be the angular velocity divided by time. But the more general case of the angular acceleration is going to be how the angular velocity changes, so that's going to be the final angular velocity minus the initial angular velocity divided by time. And so this one should have units of either degrees per second squared or radians per second squared. In this simulation, we're going to see what it takes to make something move in a circle. So you see that there's two arrows, there's the motion and there's the force. So if the force is pointing in the same direction as the motion, let's see what happens. It moves in a straight line. It speeds up and it moves in a straight line. Now let's look at another case. Let's say that the force is directed 90 degrees to the direction of motion. So you're moving to the right, but you feel a force pointing perpendicular to your motion. So in this case, 90 degrees. Let's see what happens here. So if you notice there, it moves in a circle. So what it takes to make an object move in a circle is that you have to have a force that points perpendicular to your motion. And this is the same mechanism that keeps the Earth orbiting the sun. First, if you notice the force of gravity, it points inwards, and the velocity of the Earth is actually perpendicular to the radius of the circle or of the orbit. So if I fast forward this, maybe zoom out some, you notice that the Earth is moving around the sun in a circle, and the force is pointing towards the center of the circle, but the velocity of the Earth is pointing perpendicular to the radius of the circle. So let's look at the path. So you can see it again here. The Earth is moving in a circle. The velocity is perpendicular to the radius of the circle, but the force is pointing towards the center of the circle. So because that force points towards the center of the circle, we're going to call that the centripetal force. All right, so now let's describe what we just saw in the simulations. So first of all, let's say that you have, let's take this to be the sun at the center here, and you have the planet orbiting the sun, or a car moving along a circular path, but a general particle moving along a circular path. And a circle is going to have a radius r. So as we saw, anything moving in a circle, the velocity is always going to point perpendicular to the radius of the circle. And let's say that this point here is going to make one full cycle. So it's going to travel across over the circumference of the circle along this distance here. And so the distance that point travels is going to be equal to the circumference of the circle. So the distance traveled is going to be 2 pi r. And we're going to define the time for the particle to make one cycle to be the period. Well, I'll give you the variable. We're going to define that as capital T, and capital T, we're going to call that the period. So now we can get another equation for the velocity. So the velocity of a particle moving on a circle, you can get it as the distance traveled is going to be the circumference, which will be 2 pi r, and divided by the time to make one full cycle, so that's going to be the period. Now let's see how we can include force into this equation, because what is causing this particle to move in a circle? So let's say again that this is the center here. You have the planet orbiting the sun. So the planet wants to fly away and move off in a straight line with the velocity v. But what keeps the planet from flying away in our example is going to be the force of gravity. And the force of gravity is pulling the planet towards the sun. And that force is always going to point towards the center of the circle. So we're going to call it the centripetal force. And also this planet is going to have mass m. And one more thing is we're also going to define the radius of the circle. So we can relate all those terms, and the force that keeps the planet moving in a circle is going to be defined by the mass of the planet, the velocity of the planet raised to the second power, and divided by the radius of the circle. Remember that this velocity has to be perpendicular to the radius of the circle. So this is called the centripetal force.